All right, Science 20, we're going to just pick right up where we left off last time. We're going to be talking about position time graphs. Now, position time graph is going to be important. It kind of wraps up everything that we've been talking about these last couple of videos. Keep in mind, position is a vector quantity, so we're going to include direction in with this. And so basically, our graphs are always going to be titled whatever we have on the y-axis versus whatever we have on the x-axis. So in this case, a position is going to be on the y-axis here, and time is going to be on the x-axis. Now, it's also important that when we include our labels, we're also including units with them, like I'm doing here. So display position in meters versus time in seconds. So let's just kind of jump into what some of these things are going to look like. So here on this basic graph, we see that the position is going to be at 5 meters north of the reference point. Reference point will always be here at 0. And so for the past 5 seconds, it has stayed at 5 meters north of whatever the reference point is. So basically that means we would describe this as no movement. The object is not moving. It is stationary is another way that we could describe it. Now, let me make that look a little more like an 8. Now, in physics terms, we would say that the object is at rest. But we would also say that this is an example of uniform motion. Now, uniform motion means the rate at which the position is changing, or the velocity is staying constant. And when you're standing still, where there is no movement, that is still considered to be uniform because it is going to be a constant there for us. Okay. So let's take a look at another one of our graphs here. And in this case, I'm just going to move this over here. And sorry about this, everybody. I thought I caught all these before I started the video. So I'm just going to move that over here for now. In this case, what we're seeing is we're seeing an object moving away from the reference point. Again, the reference point is always going to be here at 0, where the two axes intersect. And as we progress, every second we are increasing our distance by 1 meter north. So we're not changing direction. So we're going in a straight line. In this case, we're going north in 1 meter for every second. So everyday language would mean that we are in motion, or we are moving at the same rate away from the reference point. Reference point, I'm just going to abbreviate as REF PT for reference point. Now, in physics term, because this line is straight and we're moving the same, we're changing position by the same amount every second, we would again, in physics terms, call this as uniform motion. However, now we can say that this is happening in a positive direction. Okay. Conversely, here we kind of see kind of the opposite. We're starting at 5 meters away, and over the next 5 seconds, we're moving 1 meter each interval, and we're ending up at the reference point where on the x, where we're at position equals 0. So again, this is we are moving towards the reference point. Whereas, as you recall, in the previous one, we're moving away from the reference point. And again, this is happening at the same rate each second. We're not going 1 meter in the first second, 2 meters in the second, half a meter in the third second. We're moving 1 meter every second. And again, as you probably guessed, in physics, this gives us uniform motion, except now it's in a negative direction, going back to the reference point. At least in this case, since we're looking at position, positive is north, we're moving south in this case. Now, what can we do with a position time graph or a distance time graph? We can calculate velocity or speed, and we do that simply by finding the slope. Now, in our data booklet, we will see that velocity is calculated as the displacement over time. But as we look at our graph, we see that our displacement is on the y-axis, our time is on the x-axis. So in this case, the rise, which is the change in the y-axis, is going to be our displacement if it's a velocity, if we're trying to find velocity. And then our time is going to be in the x-axis. So the run, the change in the position of the x-axis, will give us the time there. Now, make sure you're including direction when we're looking for velocity. However, when we're talking about speed, we could have a negative speed. That means you're slowing down, but it could still include a sign or direction. However, your final answer does not need that direction. So we can kind of consider that. So I've got a little bit of practice here for you. And just to look at this one, if we're supposed to do the calculation. And again, I apologize, I don't have rulers here to help us out here. But when we look at the diagram here where the position is staying the same, our slope calculation, in this case, since we're looking at position, our slope is going to give us the velocity, and it's going to be a change in the displacement over a change in time, which is our rise over run. And since we can tell that this is uniform motion, okay, the position is changing at the same rate, our change in delta D, in this case, we've got 5 seconds, at 5, our 5 seconds here is going to, we end up at the 3 meter mark. We start at the 3 meter mark. Oop, that was not a good line. Let me try to do a nice straight line there. There we go. A little bit better. And then the change in the x-axis is going to be, we're ending at 5 seconds. We're going to subtract from that our initial, which was 0 seconds. So our delta D is going to be 3 minus 3, which is 0. Our change in seconds is going to be 5 seconds. And no surprise, that's going to give us a slope of 0 meters per second, which means the physics description of this is that object is at rest. It's uniform motion. And it is zero velocity. Zero velocity. We would say it's not moving. It's standing still. In this one, I'm not going to go through this with you right now. I'll do it in class later. But we should be able to, using the positions in the straight line, we should be able to figure out what the change in or what the velocity is going to be based on the change in time versus the change in position. And we're going to go through the same thing. Just to give you a bit of an idea, our answer is going to be positive because we're moving away from the reference point, and it's a straight line, so our slope should be consistent. So that means we're going to end up with a uniform motion again. But as I said, we'll take a look at that in class together. Okay, so that's all I got for you today. If you have any questions, please let me know. Work on those problems that I've given you in the notes, and I will see you in our next video.